Greetings. In response to a viewer request, I'm going to try a very ambitious project here, and that is to explain electrically how amplifiers function. I'm going to base my presentation on the schematic here of a very simple amp, the Fender Champ, but what I tell you can be applied to virtually any tube amplifier. First, we have to establish some definitions and rules. Number one, what is alternating current? And it's any electrical current that fluctuates in a positive and negative direction. The height of the wave is the positive voltage, the depth or trough of the wave is the negative voltage, and the overall voltage in the current wave is the distance between the peak and the trough, which in this case would be 120 volts AC. Secondly, we need to be concerned with frequency, and that's how many of these complete waves, say let's start from trough to trough, how many complete waves are there per second. In a normal household current in the United States, it is 120 volts with 60 waves or 60 cycles per second. Second, we have direct current, and direct current does not fluctuate. It remains constant. So if we start here to draw a graph of direct current, we'll have our zero line just like we did up here with AC, but we'll have a straight line, and the distance away from that zero line tells the magnitude of the voltage, and the direction of the line tells the charge. If it's above the line like this, this will be 50 volts DC. Below the line, but a considerably shorter distance, about at 1/10 distance, is minus 5 volts DC. Third, alternating current and direct current behave differently in a circuit. AC is able to pass through transformers and capacitors. Now, it really doesn't pass through them, but let's just say that if I feed AC and DC to a transformer, only the AC will appear on the other side. It's like a magic trick. Somehow it gets from here to here. Okay, it doesn't really pass through, though. As you can see, the wires are separated. It's done through induction. Over here with a capacitor, it's the same magic trick. I apply AC and DC to one side of the capacitor, only AC will appear on the other side. So transformers and capacitors effectively block direct current and do not allow it to pass. And the fourth rule is that both alternating current and direct current can coexist within the same wire without really combining or changing each other. It's not like black and white are going to make gray. If you put alternating current and direct current into the same wire, they will come out just the same as they went in. So now, using those rules, let's take a look at a amplifier schematic, and I'm going to break it down into little discrete chunks and describe each of those, and then we'll put them all together and have an overall view of how the amplifier works. The first of those chunks will be the primary windings of the power transformer, which is where the 120 volt 60 cycle power cord is connected. That's it. This is the only 120 volt 60 cycle current in the entire amp. I'm sure many people thought it's lurking up here somewhere, but it's not. It's strictly connected to the primary winding of the transformer. We have the AC switch, we have the fuse, and of course the all-important depth capacitor. Okay, all of that constitutes the entire 60 cycle 120 volt part of the amplifier. Now over here on the right, or the secondary side of the power transformer, we have three separate circuits that will have to be discussed. Number one will be the 6 volt circuit here that provides the voltage to the filaments of the 12AX7 and the 6V6. Up here we have the 5 volt circuit that provides the filament voltage for the 5Y3 rectifier. And here in the middle we have the high voltage winding that is going to end up providing the very high voltage we need for the plates of our tubes. Now I'm going to draw out each of these circuits individually and explain them to you. Okay, let's take a look at the first of the little bite-sized pieces. The first will be here the 6 volt AC circuit. Now this is on the right side, this is the secondary side of the transformer. Now over here on the left side, we have the 120 volt winding that we plugged into the wall. The reason that we have 120 volts over here, and it turns into only 6 down here, is that for every one winding we have in this coil, we have 20 windings over here. So there's 20 times as many coils on the left as there are on the right. When you plug in the 120 volt AC primary, the voltage then is dropped to 1/20th because of the 1:20 winding ratio, and we end up with only 6 volts on this side. That's where transformers get their name. They transform 120 volts into other usable voltages, in this case 6 volts of alternating current. This winding is fairly stout. It can usually handle like 2 or 3 amps of current, and if you look, all it's used for is just like a string of Christmas tree bulbs. For those of you who observe Christmas, we've got 3 bulbs here. They're just like light bulbs, and we're sending one side of the 6 volts AC into one side of the heater of the tube, and that's all it is. It's a filament just like a light bulb, and when you plug in your amp and turn it on, this is what you see glowing red, is that. And if you have a pilot light and it lights up, it's that. So all these are a series here of heaters in the tubes. We run the electricity in here, it runs through, and in this case, because it's a 12AX7, there's 2 heaters. Here's one right here, and here's the other. So 6 volts comes into this heater, 6 volts comes into this heater, and we add them together. 6 plus 6 is 12, and that's where the 12 AX7 gets its name. Okay, so we have 12 volts of heat in here, heating up the cathodes. We'll talk about that in a second. I've got 6 volts in here to the heater of the 6V6. Notice that the first number of the tube matches the voltage of the heater, and it's heating up the cathode. And then over here, I've got 6 volts that's making this glow and tell me that the amp is turned on. Now, why do we do this? Well, we don't care if the tubes glow or not. It's not to make a pretty display. It's to heat up this unusually shaped device in here called the cathode. And it's like the frying pan sitting on the burner. We turn on the burner, and you know how on electric range it gets red hot? Well, so does this. This heater is going to get red hot. It's going to heat up the frying pan, but instead of cooking eggs or ham or something like that, we're going to cook the cathode and make it release electrons. I think of it as almost like I've got a pan here of popcorn, and as the heat builds up, the popcorn starts popping and the electrons start flying off in all directions. Now, I don't want to get ahead of myself here, but you know that electrons are negative, and they want to go to something that's positive. So let's be real tricky, and we're going to, and like I said, I'm ahead of myself here, but eventually I'm going to charge this thing up here positive, and it's going to attract those electrons. They're going to want to flow up here to this. This is the plate. Okay, so the popcorn's popping off here, and I've got a real strong vacuum cleaner running here, and the popcorn really wants to go to it. Then, just to be sneaky, I'm going to build like a chain link fence between the frying pan and the popcorn and the plate where the vacuum is. And I build this chain link fence in such a way that I can open and close the holes and make the fence more or less porous. So using the grid, which is what this dotted line is here in the middle of the tube, I'm going to let the electrons, either more or less of them, flow to the plate. Okay, let's just leave it at that for now. We're going to pick up and enlarge on that in a few minutes. But in conclusion, let's take a look. The 6-volt AC winding, all it exists to do is heat up the heaters in the tubes, which in turn heat up the cathodes and make electrons come boiling off the surface of the cathode. Also to illuminate the pilot light so we know the amp is on. Now let's look at our second little bite-sized piece, and that is the 5-volt AC circuit. Remember, it was right up here at the top in our champ schematic. Now, first off, let's look at what the winding ratio must be to drop 120 volts AC to 5 volts AC. Did anybody come up with 24 to 1? Okay, so there must be 24 windings on the left for every 1 on the right, so that when we run 120 volts AC through the coil on this side, we end up with 5 volts AC on the right side, or the secondary. The other thing about this that's important is that your 5Y3 rectifier, and notice that the first number, the 5, is the same as the voltage, requires a lot of current to operate, and this circuit uses heavy wire and can handle at least 3 amps of current. So as you can see, this is fairly stout, okay, heavily wired. That's why if you're ever wiring up an amp or a new transformer, the heaviest wires of all will be those that go to the heater of the rectifier. Now, notice also this is a lot like a 6-volt circuit in that all we do is come over here and heat up the burner on the stove, and that's all the 5-volt AC circuit does. The high voltage windings, though, are a little more complicated. So let's take it kind of slow and step by step here and see if we can't figure this out. First off, the winding ratio is reversed from what we've seen. If we put in 120 volts on the left and we get 650 volts out, that's from one end of the coil to the other, I'm thinking it must be, around 5.5 times as many turns on this side as on this side. So with 5.5 times the turns over here, when I put 120 volts on the left side of the transformer, I'm going to get around 650 volts out on the right side. The other thing about this that's a little unusual is that the high voltage winding has a center tap, and that's exactly what it looks like. There is another wire connected to the coils, but right in the middle. It divides the 650 volt secondary into 2 325 volt halves. And it does one other thing, which will remind some of you of an output transformer, but backwards. It takes the 120 cycle signal, and it not only makes it 3 times bigger. Remember, we turned 120 into 325. It's almost triple. But it also, the upper winding here, leaves the pattern of the alternating current alone. Up is up, down is down. The lower part here, the lower winding, or half winding of the secondary, has the mirror image. And this is the way output transformers work also. So what's up is down, and what's down is now up. So if I hooked an oscilloscope up to this part of the winding, I would get a pattern that looked just like this, but about 3 times bigger. And if I hook my oscilloscope up to this part of the coil right here, I'm going to get a mirror image of that pattern and about 3 times bigger. Now the ends here of the high voltage winding go to the plates of the 5Y3. You notice there's no grid in the middle. All it is 2 plates and a heater. Now this acts as 2 diodes, and I'm not going to go into any depth here on what diodes are, but they're like valves. They only let electricity flow in one direction. They'll let the positive through, but they won't let the negative through. Or if you flip them over, they'll let the negative through, but they won't let the positive through. Now here's what happens here. With this being like 2 diodes, it's going to sort out these curves. And when it sorts them out, it's going to send all of the tops, top, to this wire. So we have all the tops coming out. And it's going to send all the bottoms, bottom, down here to the center tap, which we connect to ground. So if I were to hook up an oscilloscope to look at what's coming out the ground here of the high voltage winding, I've got bottom. Remember, this line right here is neutral or 0. And if I hook the oscilloscope up over here, I've got all the tops cut off of these waves. And so we have 2 outputs from our power supply. The diodes down here send all of the bottoms of the curves, bottom, which are negative, out through the center tap to ground. So the signal right here going to ground is all of the bottoms from these curves, which is all negative, and it's minus 325 volts of direct current. There's a lot of ripple in it, but it's still direct current because every single portion of this output is negative. Over here is the other output, and it is all of the tops. The tops of the curves are sent by these diodes out this wire, and we end up with this type of output. All the tops of the curves, it's all positive. Again, a lot of ripple, but we're going to take care of that. We're going to solve that with our filter capacitors and some other components in our amplifier. We will smooth these ripples out. Now, if you really want to just back off and take a look at this, it's very much like a battery. Your power supply resembles a DC battery. We have a negative terminal right here that's minus 325 volts DC, and we have a positive terminal down here that is plus 325 volts DC. If the complexities of how it accomplishes this elude you, or if you're really not even interested in the complexities, just keep in mind that this wire, minus 325, this wire, plus 325, and it is direct current. Okay, this is, I think, by far the most complex portion of the amplifier, and I'm going to stop this first segment here. We've reached the point where we have what amounts to is a direct current battery with a negative terminal and a positive terminal. We see that just like in a car, we connect the negative terminal to ground, but the positive terminal, that's something else. So you're going to have to watch part 2 to see what we do with this positive 325 volts of direct current.